there, algebra. Today we are learning Lesson 8 in our Unit 5 on exponential functions. Let me write down what we're doing today. All right, there it is. We're going to determine and explain orally and in writing whether relationships in descriptions, tables, equations, or graphs are functions. Okay, are they functions? And we're going to determine and be able to explain. Okay, I need you to be able to, both by words you speak and by words you write down, okay? So let's get into it. I have to sneeze. Sorry about that. Here is a graph of the accumulated rainfall in Las Vegas, Nevada in the first 60 days of 2017. Okay, use the graph to support your answers to the following questions. First of all, is the accumulated rainfall a function of time? Okay. Here I just look at my x-axis and we have days of the year in 2017 and the rainfall in inches. So is the accumulated rainfall a function of time? Well, yes, it is. Why? Okay, so for each, we can say for each, they didn't leave much space here, did they? That should be number. For each number of days, we'll say that's D. Between, I see 0 to 60. A certain amount of rain fell. Okay, so I've always said 1 to 1. So we can say for one day, there is one amount of rain. Okay, one day, one amount of rain. Okay, that's 1 to 1. All right. Now, is time a function of rainfall? No, it doesn't work that way. No, it's not. Okay. If we look at that, there was no rainfall for the first 10 days. So if I looked at 0 rainfall, that's not just day 1. That could be anywhere from day 1 to 10. So I couldn't say, hey guys, what day was there 0 rainfall? And you can only give me one answer. You couldn't do that. You'd have to give me a range of answers. Well, Miss Carly, I'm not sure. It could have been 1 day, it could have been day 9, etc. So it's not 1 to 1. That's the important part. That's how we test it. Not 1 to 1. Okay. Oh, hold on. Let's get rid of that. Okay, moldy bread. Last night for dinner, I pulled out a cube of cheese that I needed to shred for our dinner, and it had mold all over it. You just look at it and you're like, oh. And I think my dad would have cut off all the mold and still used the cheese. My husband threw it away. It wasn't that much, but it's sad to throw away things that are moldy. Okay, so here we are. Claire noticed mold on the last slice of bread in a plastic bag. The area covered by the mold was about 1 square millimeter. That means it's just 1 millimeter by 1 millimeter. Okay? And that's even too big, but 1 square millimeter is the area It's about 1 millimeter by 1 millimeter. She left the bread alone to see how the mold would grow. The next day, the area covered by the mold had doubled, and it had doubled again the day after that. So if the doubling pattern continues, how many square millimeters will the mold cover 4 days after she noticed the mold? Show your reasoning. Well, you guys know how to write an equation now. We could say the mold is equal to the initial amount times doubling each day. Okay? So if the doubling pattern continues, we could just do the pattern, which is day 0, then day 1 doubled, day 2 doubled, day 3 doubled, day 4 doubled. Or we could use the equation. The amount of mold equals the initial amount times doubling to the 4th power, which would also give us 16. So it's 16 millimeters squared. Okay? So represent the relationship between the area A in square millimeters covered by the mold and the number of days D since the mold was spotted, using a table of values showing the values from the day the mold was spotted through 5 days later, which I just kind of did, but that's okay. So we have days D and we use A. And I see you guys doing this on your homework, but remember the first value we put in there is day 0, which is the initial amount. So day 0, we have just 1. In day 1, we double it, we double it, we double it, double it, double it. And this is days and millimeters squared. Oh goodness, excuse that. Sorry, my daughter must be packing her lunch. All right, so that is a table representation. All right, now how about an equation? We already made one. So the area equals the initial value. We're doubling it raised to the day. So that's your representation with equation. And then a graph, which we don't have a coordinate plane. So we'll make one. We have days, 1, 2, 3, 4, 5, and then area, which would be millimeters squared. We go anywhere from 1 to 32. So let's go by 5s. 5, 10, 15, 20, 25, 30, 35. So day 1, well, day 0 we're at 1. Day 1 we're at 2. Day 2 we're at 4. 1, 2, 3. Day 3 we're at 8. 5, 10, just a little less. Day 4 we're at 16. 5, 10, 15, 16. Oh my goodness. I'm sorry. Day 5 we're at 32, which is all the way up here. All right. So that's 3 representations. Now discuss with your partner the relationship between the area covered by mold and the number of days of a function. I am one popular person this morning. I can't turn that off right now. Discuss with your partner, is the relationship between the area covered by mold and the number of days a function? If so, write blank is a function of blank. If not, explain why it's not. Well, yes, it is. And you're my partner, I'm your partner. So we can say the area covered by mold is a function of the number of days that have passed. Fancy way to say it. You may not come up with anything as eloquent as that. It's not eloquent. but it's all good. So really we're going to say anything about area is a function of time. Okay, that works. All right. Lesson 8. Are you ready? Bonus. Okay, functionally speaking, here are some situations we have seen previously. For each situation, write a sentence in the form blank is a function of blank. Okay, so for each one of these situations, we're going to write a sentence. We're going to indicate which is the independent and which is the dependent. I always think the independent is the one that you plug in, and the dependent is the one that comes out. And then write an equation, okay? My morning duty starts in 6 minutes. I may have to pause and come back. So, in a biology lab, the population of 50 bacteria reproduce by splitting. Every hour on the hour, each bacterium splits into 2 bacteria. I'm going to do this one straight away, but with number 2 and 3, it'd be great if you would pause the video and try it on your own. Okay, so we can say, first bullet, the number of bacterium is a function of time passed in hours. Okay, next we can say that the independent is the number of hours. Time is always the independent one. You think about independence. That's you're making your own way, you're doing your own thing. That's time. Time doesn't stop for anyone. It does its own thing. It's very independent. And then our dependent is the number of bacteria. And then our equation would be, I could use anything. Let's see. Bacteria at a certain time is equal to, let's see, 50 is our initial amount, and we're doubling. All right, that's simple. Okay, this next one, every year a new car is purchased, it loses a third of its value. So it loses. I'll give you a hint. You have to figure out how much is remaining. Let's say the new car cost $18,000. Now, I really would challenge you to push pause and see if you can figure it out on your own. All right? So push pause, and I'll push pause too, and we'll come back. All right. So this is a function. The value of a car is a function of years since purchased. Our independent is still the time, so the number of years since purchase is independent. And then dependent is the value of a car. Think about dependent. The value of the car depends on how many years since it's purchased. Okay, so independent is the number of years, dependent is the value of the car. And then my equation, my function is the value evaluated at y. So V of y is 18,000 times 2/3 t. That's the amount remaining. We lose a third of it, there's 2/3 remaining. Okay? Okay, this last one. Again, push pause and try it on your own. I'm going to be a minute late for my morning duty. All right, here we are. So in order to control an algae bloom in a lake, scientists introduce some treatment products. The day they begin treatment, the area covered by algae is 240 square yards. Each day since treatment began, a third of the previous day's area remains. Time is measured in days. So our function sentence would be the area covered by the algae is a function of the days since treatment. Independent, again, is the time, which is the number of days in this case, and the dependent is the area of the algae. And our function will be A of D equals 240 times 1/3, which is how much is remaining, times t. Okay, we're going to pause. Be right back. All right, let's get this done. Deciding on a graphing window. So the equation m equals 20 times 0.8 to the h models the amount of medicine in milligrams in a patient's body as a function of hours after injection. Without using a graphing tool, decide if the following horizontal and vertical boundaries are suitable for graphing this function. So our input is h. So that's going to be the x-axis. That's hours, right? Yes, and then this would be the amount. Our initial amount is 20, and it gets smaller every time. So the maximum is really going to be 20, and we're going to get smaller every hour, okay? I don't know how much, but our hours, I mean, if it's 0.8 remaining, I don't think it's going to be very big. I think 100 is probably too small, but what they're saying is -10 to 100. All right, but for the medicine, going up to 1,000 is a no, because the maximum amount of medicine we have is 20 milligrams. So I don't need a maximum of 1,000. That's just way too big. I don't even need a -100. Oh, there's two O's and too big. So this is too small. So that's just crazy. And really, 100 hours, yeah, the more I think about that, that's way too big. I doubt there's anything left in the system. We can take it down to 10, maybe even 20, and it would make better sense. Okay, so really, this is the max amount of medicine. We're not sure about the hours. I don't think I need -10, maybe a -1, just so we can see the axis, and a -1. Just so we can see that 0, 0. Yeah, so to talk out loud, that's what I would do. Verify your answer by graphing the equation using graphing technology and using the given graphing window. What do you see? All right, let's go over to Desmos. So we are at y equals 20 times 1/8, no, 0.8, 8/10 to the raised to the x. Okay, here's how we change our window. So if we do the one that's given, it was hours go from -10 to 100, and medicine goes from -100 to 1,000. All right, not useful. This is where all of our data is, and it looks like we're at 0 pretty quick. All right, so that is not useful at all. I am certain that the highest y value we need is 20. Wait, let's just do 25 so we can see just below that. And the y-axis, I don't really need to see any of it. So that looks much better, but I think our x-axis is still, let's see what 10 does. Oh, 10 is not big enough. So what? Why isn't 10 big enough? I can't see where it really gets down to 0. So I need more x-axis, like more cowbell, but not as much fun. So we start up here at 20, and we are decreasing, and it looks like down here, we're pretty close to 0 because that's 1. I could take that a little bit more if I wanted to. I'm kind of happy with it. Yeah, even if I double it to 40, okay, we're down to 0, about 25. So we could say 30. Right, that right there is a graphing window that is much more acceptable, okay? Yep. Seeing if there's anything else. I think that's it. Check and check. Here's your summary. It's fantastic. Okay, great thing to study for your any assessments. All right, have a great day.